A single machine like this can generate enough electricity to power thousands of homes for an entire year. Its huge blades can exceed 300 kilometers per hour. But how does the power of the wind turn into electricity? In this video, we're going to find out how a wind turbine that generates electricity works. Wind turbines are so monumental that their blades can be over 100 meters long and sweep an area larger than several football fields. If one of them were placed vertically, it would be taller than many 30-story buildings. Despite their colossal size, they are made with ultralight and extremely resistant materials, such as fiberglass and carbon fiber, capable of withstanding years of exposure to storms, torrential rains, and extreme temperature variations. Although the rotor seems to spin slowly, the tips of the blades can reach speeds over 300 kilometers per hour, faster than many high-speed trains. But moving structures of this size is a gigantic engineering challenge. Each blade can weigh more than 50 tons and needs to withstand the intense forces generated by the wind. That's why they're designed to flex, just like airplane wings during flight. Operating at maximum capacity, a turbine can generate between 3,000 and 7,000 kilowatts of electricity per hour. That amount of energy would be enough to power about 3,000 to 5,000 homes over the course of a year. When the wind hits the turbine, it strikes those giant blades. And although it seems like they're just being pushed by the air, the process is much more complex. The blades have an aerodynamic design very similar to that of airplane wings. Their precisely calculated shape makes the airflow faster on one side than the other, creating a pressure difference that generates a strong lift force. This force is the real reason the rotor starts moving. The three blades are connected to a huge central piece called the hub. When the wind blows, the rotor starts to turn slowly. Although the tips of the blades reach speeds of over 300 km/h, the rotor as a whole moves at a surprisingly slow pace, usually between 10 and 20 rotations per minute. However, even at this seemingly modest speed, the accumulated energy is colossal. The movement of the rotor is transmitted by a robust main shaft to the nacelle, that large structure located at the top of the tower. This veritable operation center houses some of the most complex and valuable components of the entire facility. Inside it are electronic systems, safety brakes, smart sensors, hydraulic mechanisms, and the electric generator. The mechanical energy generated by the rotor first passes through a huge speed-increasing gearbox. It's one of the most impressive and complex components of the entire turbine. This gigantic set of high-strength steel gears works similarly to a car transmission, but on a monumental scale. Although the rotor captures a huge amount of energy, it spins too slowly for the electric generator to work efficiently. After all, generators need much higher speeds to produce electricity on a large scale. That's where the gearbox comes into play. Inside it, several sets of gears work in perfect sync to gradually increase the rotational speed. A rotor that moves at 15 revolutions per minute can come out of the gearbox spinning at about 1,800 revolutions per minute, which is 120 times faster. This increase allows the generator to reach the ideal conditions to produce electricity in a stable and efficient way. The forces supported by this mechanism are extraordinary. Each gear needs to transmit immense amounts of power while dealing with loads caused by the constant fluctuations of the wind. The gearbox is able to handle thousands of horsepower continuously for years. That's why the gears are made from special steels that undergo heat treatments to drastically increase their hardness and wear resistance. In addition, the entire system is submerged in hundreds of liters of lubricating oil, reducing friction, dissipating heat, and extending the lifespan of the components. That's where the real technological magic happens. Inside the generator, there are large magnets and copper coils. When the magnets rotate around the coils, they generate a variable magnetic field that forces the electrons in the copper to move. This movement of electrons is exactly what we call electric current. This is the same physical principle discovered by Michael Faraday almost 2 centuries ago, and even today, it is the basis for practically all electricity generation in the world. But modern turbines don't just spin and produce energy. They are equipped with a sophisticated network of sensors capable of constantly monitoring the wind speed and direction, ambient temperature, structural vibrations, and even the presence of ice on the blades. Thanks to these intelligent systems, the nacelle can automatically rotate to always stay aligned with the wind direction, optimizing energy generation. In addition, each blade can adjust its pitch independently. When the wind is weak, they adopt a position designed to capture even the slightest breeze. When the wind becomes too strong, they change their angle to reduce the load and prevent structural damage. After all, as contradictory as it may seem, too much wind can also be a problem. A wind turbine doesn't operate indefinitely at any speed. Normally, it starts generating electricity when the wind reaches between 10 and 15 km/h, and its output increases progressively until it reaches maximum power, usually between 45 and 55 km/h. However, if the wind exceeds speeds close to 90 km/h, the safety systems are activated and completely shut down the machine to protect it. The danger arises when the emergency braking system fails during a storm. In this situation, the blades spin so fast that the aerodynamic loads and centrifugal forces can exceed the structural limits of the design. A blade that normally spins with its tips at around 300 km/h could reach much higher speeds. At this rate, even a small crack or structural defect would spread quickly, leading to the collapse of the entire structure. But the electricity generated is still not ready to reach our homes. Although it has already been created by the movement of the giant blades, it still needs to go through a series of electronic systems that prepares it for the long journey through the power grid. The first step is to go through the power converters. These sophisticated systems act as real electrical translators. Their mission is to adjust the frequency and voltage of the electricity generated so that they match exactly the requirements of the grid. Without them, the energy produced by the turbine would be too unstable to be safely integrated into the electrical system. Next, the current reaches one of the most important components of the entire facility, the transformer. Although it seems like a simple piece of equipment, its function is fundamental. The electricity leaves the generator with a relatively low voltage, usually a few hundred volts. If we tried to transport it this way for dozens or hundreds of kilometers, a large part of the energy would be lost as heat. To avoid this, the transformer drastically increases the voltage. By increasing the voltage and reducing the current, energy losses decrease dramatically. The difference is impressive. A turbine can generate electricity at hundreds of volts, but after passing through several transformers, that same electricity can travel through transmission lines at 220,000 or even more than 400,000 volts. Once transformed, the electricity leaves the wind farm and begins a journey that can stretch for hundreds of kilometers. During this journey, the energy passes through several electrical substations where the voltage is gradually adjusted. First, it is reduced for regional transmission, then for urban distribution, and finally down to the voltage used in household outlets. The most impressive thing is that this whole process happens almost at the speed of light. From the moment a gust of wind makes the blades spin, the electricity reaches the power grid almost instantly.